Hello, welcome to Hey Solutions channel. In this video, I'll be discussing the application of Lagrange equation in the formulation of equations of motion for a vibrating system. And we're going to look at two examples quickly. And to begin, I want to talk about the Lagrange equation itself. This is the formulation for the Lagrange equation where there are different terms. L there means T minus V. It's called the Lagrange formulation, and that's what you apply. So the first objective usually is to determine the Lagrange formulation, where V is the total potential energy, T is the total kinetic energy, and we have QI. QI is what you call generalized displacement. Then QI dot is called the generalized velocity. That later on, as we look through an example, we see what we mean by this. Then we have what you call QI, that's capital Q, to be the generalized force acting on the system, and is obtained using the equation dW dI. It is usually the force that is as a result of the work done in dissipating the energy of vibration in the system. Here, W is the work done in dissipating energy from the system. Of course, there's a simple formula for estimating work done when you have damping, and that's the formula. We'll see how to use it later on. The Lagrange formulation could also take this form, the T, the Q. There are different forms, but I always advise people to stick to the first form because it's just straightforward and it's one way throughout the equation. The Lagrange equation can also take this form. So whatever form you're familiar with, it's all the same thing. Then how do we apply the Lagrange equation? To apply the Lagrange equation, first you need to determine the number of degree of freedom and all the generalized coordinates of the system. That's how many degree of freedom do we have on the system. Then what are the generalized coordinates? Then after that, you need to determine the total kinetic energy in the system. Then you proceed to determine the total potential energy. Then after that, you determine the total work done due to damping on the system. Then you derive each of the equation using the Lagrange equation for each of generalized coordinates. So if we have this system, we talked about it before, one can easily tell it has 2 degrees of freedom. That mass M1 can be made to be vibrating horizontally without affecting the vibration of mass M2. So we can say the generalized coordinate of M1 to be, can take it to be x1, while the generalized coordinates for the mass M2 to be x2. So we're going to proceed to quickly solve this problem. So to solve this problem, we first need to identify the generalized coordinates. For this case, we have them as x1 and x2, and we have our degree of freedom. Degree of freedom is 2. And what does that mean to us? That means that I is equal to 1 and is equal to 2. Such that when you have QI, you are referring to I to be equal to 1 and 2. Then the next thing we may want to call our Lagrange formulation, which we are supposed to use to solve this problem. And by our Lagrange formulation, we have that the T of the L, the QI dot minus the L, the QI is equal to the generalized force, capital QI. Our first struggle then becomes, what is our L? I will know that L is equal to T minus V. And as a result of that, we need to find what T is, total kinetic energy, and what is the value of your total potential energy, V. T is equal to unknown. So if we want to find T, we have to find the kinetic energy as a result of inertial movement of each of the mass, M1 and M2. So we have that T is equal to Our kinetic energy we know from basic physics to be half mv squared. But for this case, we will be using our generalized coordinates. So we have half m1. Instead of it to put mv squared, we use x1 dot square, where x1 dot signifies displacement, derivative of displacement with respect to time, which is also velocity. Then total kinetic energy, we also need to add the other components. That's the kinetic energy of the second mass, m2, multiplied by x, this case x2 dot square. And having gotten our total kinetic energy, the next struggle becomes to get our total potential energy, V. Total potential energy is equal to the potential energy of all of the spring acting in the system. For this case, we have half the first spring, K1, will be half K1. Energy of the spring is half Kx square. That's half K times displacement square. So we have half K times x1 square for the first spring. Then for the second spring, we have half times K2. For this case, the displacement of this spring, K2, is a function of how far this mass has moved and how far this mass has moved. So as a result of that, the displacement becomes the difference between the two displacements, that between the difference between the displacement of the two masses, which is supposed to be x1 minus x2. So for the case of K2, we have that V is equal to half K2. Here we have x1 minus x2, and the whole of this displacement, we take it as square. And there's no other mass in the system. There's one other term we may need to calculate, and that's our work done. We have a damper, we have damping in the system. And damping in the system, as you can see, C1 here, is as a result of this displacement, this generalized coordinate x1. And we have that work done is equal to minus integral. So we have our displacement, let's say 0 to x1, as this case is here. We are going to integrate C1, which we have there, multiplied by S1. Then we're integrating this with respect to our displacement S1. So having calculated for T and V, the next goal becomes to look for your Lagrange formulation. That's your Lagrange function, L. And we said L is equal to T minus V. And T and V are already known. So we have that L is equal to T, which is half m1 x1 dot square plus half m2 x2 dot square minus V, which is minus half k1 x1 square plus half k2 x1 minus x2 square. Once L is gotten, then we may begin to look for the different equations of motion considering each of the generalized coordinates per time. So we are taking our first generalized coordinates, that's for I equal to 1. We have that Q1 is equal to x1, and Q1 dot Q dot 1 is equal to x1 dot. And of course, we are going to look for the generalized force, which is equal to the Wi, that's the W1, the x1. So taking all this per time, let's quickly find our generalized force first. We have that Q is equal to the W, the x1, which is equal to D, the x1, into minus integral 0 to x1 c x1 dx1. This is equal to, we know that because you have integral here, with respect to ds, and we're differentiating this with respect to ds, the differential will cancel out the integral term such that qi will be equal to minus cs1. To continue, we also need to find other terms. And to find the equation proper, let's recall our Lagrange equation as it applies to this first generalized coordinate. We have that d dt into dl dx1 dot, that's q1 dot, minus dl dx1, that's q1, is equal to qi. We've already gotten qi from our equation here. We've gotten qi, so the other terms we need to look for is this first term of the equation and this other term of the equation. Let's remember that we've gotten our L earlier. Let's recall that our L is equal to half m1 x1 dot square plus half m2 x2 dot square. Then we have minus half k1 x1 square minus half k2 x1 minus x2 square. So if we have this, we want to begin to look for the different terms of the Lagrange formulation. The first term we want to look for is the L ds dots. If you do that, so that we can find the basic term, let's not forget our Lagrange formulation, d dt dl dx1 dots minus dl dx is equal to qi. So we want to look for dl dx1 dot so that we can find d dt of that value. To do that, we have that dl dx1 dot means differentiate the whole of your L terms. Every term you have in the L, differentiate them with respect to x1 dots. And if you look at the equation critically, you won't see x1 dot anywhere except the first term, except in the first term, which is this part. This is the only place we have x1 dots. And because we have x1 dot there, if you differentiate that, you're likely going to get 2 times half times m1 times x1 dot. If you check out this term, there's no x1 dot. Check out this term, there's no s1 dot. Check out this term, there's no s1 dot. So we have plus 0. And this implies that if you are to differentiate this with respect to time, dl dx1 dot, we are going to get, that's differentiating this, so we're going to get the d dt into m1 x1 dot. Let's not forget that dl dx1 is this term. 2, we cancel 2, so what will be left is m1 x1 dot. And if you differentiate this with respect to time, knowing that mass is constant, you get m multiplied by s1. There's dots, the differentiating with respect to time just to add another dot. So d dt dl dx1 dot is equal to m x1 dot dot. And dl dx1 is the next term we want to look for. It means we have to differentiate the whole of the L, the Lagrange formulation, with respect to x1. What are the terms containing x1? Let's quickly look at it. You discover that the first term has x1 dot square, no x1. The second term has x2 dot square, no x1. The third term correctly has x1. So if we differentiate this part, we have for other parts to be 0 minus 2 times half times k1 x1 minus, if you differentiate this part also has x1 in it. So if you do that, you have 2 multiplying half k2 into x1 minus x2. Then if you differentiate the inside, which is called the core, you have multiplied by 1. And as a result, if you simplify this, you're likely to get k1 x1 minus k2 x1 minus x2. And if you bring the equation together, let's not forget that we've gotten qi before to be equal to minus cs1. You bring the equation together in the Lagrange formulation, which is d dt dl dx1 dot minus dl dx1, which is equal to qi. We have that. Let's not forget what our d dt dl ds1 is. That is what we obtained there earlier. So we're going to get in our equation m1 s1 dot dot. Sorry, this is m1. Forgot to put that one before. Minus dl dx1, which is this part that we got earlier. So if you bring that in, minus, multiply minus, and we'll change that to plus. This sign will change to plus k1 x1. Likewise, the other sign will change to plus k2 x1 minus x2. The whole of this is equal to qi, and we'll obtain qi before to be x cs1. So as a result of that, we can rewrite our equation to be m1 s1 dot dot plus k1 x1 plus k2 x1 minus s2 plus, sorry, this is supposed to be minus, which we got earlier, plus c s1, which is equal to 0. And this is our first equation of motion. To get the second equation of motion, we are going to start by calling forth our second generalized coordinate. That's when I equal to 2. q2 is equal to x2, and q2 dot is equal to x2 dot as well. And likewise, capital Q q2 is equal to the w2 over the s2. For this case, there is no damping attached to the second mass, so we have our w2 is equal to 0, and likewise q2 is equal to 0. Then the next thing to do is to call forth our Lagrange formulation, which we know that d dt. For this case, we'll take dl dx2 dot minus dl dx2 to be equal to q2. Our concern therefore becomes, how do we get each of these terms? We've already derived our Lagrange formulation L earlier to be, which is t minus v, to be half m1 x1 square dot plus half m2 s2 dot square minus half k1 s1 square minus half k2 s1 minus x2 square. So to look for each and all of the term, we're going to start by looking for this term that is inside these brackets, dl dx2 dots. So to determine dl dx2 dots, we are going to differentiate the whole of x with respect to x2 dots. So if you look through all terms, you see that there's no s2 dot term here. There's no x2 dot term here. Okay, there's s2 dot term here, just here. There's no x2 dot term here, and there's no x2 dot term here. So if we were to work with this, we have that the L, the x2 dot becomes 2 times half times m2 x2 dot. Then every other term is 0, minus 0. This implies that the dt, the L, the S2 dot is equal to d dt, because we've estimated the L, the x2 dot earlier, d dt m x2 dot. And the reason for that is because these two, we cancel out these two, we'll be left with m2 x2 dots. And if we differentiate this with respect to time, considering that mass is constant, that's our mass m2, let's not forget this is m2, mass m2, we have x2, differentiating with respect to time, we just take this as another dot. So we've gotten our value for the dt, the L, the x2 dots. So we're going to look for the second term, the L, the x2. So the L, the x2 means differentiate the whole of the Lagrange function which we had here with respect to x2. The first term does not contain any x2. The second term does not contain x2. What it has is s dot 2. The third term does not contain x2, but the fourth term do. So it's just this term that has s2. So if we're differentiating the whole of this, we're going to get 0, 0 minus, 0 plus, minus 0, minus, then when we differentiate the last term, we have 2 multiplying half k2 multiplying x1 minus x2. And if you want to simplify this further, you see that 2 will cancel 2. Then mind, if you differentiate the inside, we are going to get minus 1. And the reason for that is just differentiation of function of a function. When you're differentiating a function of a function, you differentiate the power first, then you differentiate the core. That's what you have inside. And this will be equal to the minus, we cancel out this minus we cancel out this minus. And what we have at the end of the day is going to be k2 x1 minus x2. So we've gotten all terms in your Lagrange formulation. All the terms has been gotten. So if we write out our Lagrange formulation again, d dt, the L, the x dot 2 minus the L, the x2 is equal to qi. Having gotten all the terms, we can have therefore that, knowing that this first term, d dt, the L, the s2 is equal to what we got here, m2 s2 dot dot. So we have that m2 s2 dot dot minus, then we take in the second term, which is the L, the s2, which is what we got here, minus k2 s1 minus s2 is equal to qi, for this case q2. And we started by calculating q2. We had that q2 is equal to 0 from the beginning. So the whole of this will be equal to 0. And this can be rearranged to be m2 s2 dot dot plus k2. If you take this minus sign inside, this will turn to minus and this will turn to plus. So we have s2 minus s1 all is equal to 0. And this is your second equation of motion. And because it's a 2 degree of freedom system, we can have just 2 equations. And this is the second equation of motion for the system. I do hope that you found this video helpful and it is clear enough. I hope to bring out another video on Lagrange formulation where some of these concepts will be further explained. I want to thank you very much for watching, and I hope to see you next time.